Welcome to the Crazy Head Chemist. So today we're doing another video in bonding and molecular structure. Bam! Today we're doing the resonance structures for carbon dioxide. So what is the formula for carbon dioxide? It's a binary non-metal compound that is binary, two atoms, non-metals, using prefixes. That's why it's dioxide. CO2. You're going to look in your periodic table and you're going to get the number of valence electrons for carbon and for oxygen. Bam, beautiful. Now draw resonance structures. Okay, now you might be familiar with drawing carbon dioxide already. Now what I want you to do is I want you to take that Lewis dot structure and I want you to come up with two more different resonance structures, two more different Lewis dot structures that are equally valid. Well, maybe not. Okay, so here's one of them. By the way, this one works. Why? Because the octet rule is still there. This one also works because the octet rule is still there. And this one is the one that you are probably most familiar with. Okay, there are arrows in between each one of these. Notice that these do not have brackets. They don't have brackets because they don't have a negative charge, because this is a molecule that does not have a negative charge. Some people might want to put brackets around all this stuff without a negative charge or a positive charge up above, and that would be okay, but you really need the arrows. Okay, any one of these is AX2. That's 2 bonding and 0 non-bonding regions. Any one of these is also linear. The bond angle is 180, and this molecule is nonpolar because it has symmetrical dipoles. Now, that is a true statement. Let's figure out that that is perfectly a true statement. The bond order for any one of these is the number of bonds. That is a 1, 2, 3, 4. In the number of regions, that is actually 2. So it doesn't matter which one of these resonance structures you're looking at, you're going to get a bond order of 2. Okay, now I'm hoping that you were able to come up with those two other resonance structures because they are valid, because they do validate the octet rule for either of the oxygens and that carbon in the middle. That is critical. Okay, now how do you distinguish between all three of these resonance structures? The answer is formal charge. Okay, that is how you distinguish between non-equivalent resonance structures. So let's get the formal charge for each one of the atoms and each one of the resonance structures. So I want you to get these numbers on your own. That's the number of valence electrons minus 1/2 of the bonding electrons minus the lone electrons on that atom. Okay, so here we go. The formal charge for this left-hand oxygen in that left-hand Lewis dot structure is +1. Is that a good thing, by the way, or not a good thing? I guarantee you that's a bad thing, because oxygen is electronegative, so ideally all elements should have a formal charge of 0. However, if an element does have a formal charge, the most electronegative element, that would be oxygen compared to carbon, the oxygen should have a negative formal charge. And this one has a positive formal charge. No bueno, man. No bueno at all. Okay? The central carbon has a formal charge of 0. That's a good thing. That's what we want. That right-hand oxygen has a formal charge of -1. Now that is perfectly acceptable, and you will find a lot of oxygens that have a formal charge of 0. Sorry, a formal charge of -1, and that's perfectly acceptable because it's the second most electronegative element, so it should have a negative formal charge if it were to have a formal charge. All right. So let's look at this middle structure. Formal charge of -1, formal charge of 0, formal charge of +1. You should see that these formal charges, I'm not going into much detail, but it is truly the flip, or the reciprocal, if you will, of the left-hand Lewis dot structure. Now let's take a look at this far right-hand Lewis dot structure. The formal charge of this oxygen is 0. The formal charge of the carbon in the middle is a 0, and the formal charge of the right-hand oxygen is 0. So which is the predominant Lewis dot structure? And why is the carbon dioxide molecule non-polar? Because it is symmetrical. And that's why I'm going to circle this one. It is most certainly symmetrical. Okay, and it is nonpolar, and that is the predominant Lewis dot structure. Now, If you were just going to do a Lewis dot structure for carbon dioxide, that would be the one that you would draw. Why? Because of formal charge. Now, if your instructor or professor says, hey, maybe you need to draw other Lewis dot structures of carbon dioxide, then you're going to draw the other ones. But how you distinguish is formal charge. It's a formality, and there is a charge to it. Wait, it's for free, actually, as long as you know how to do the math. Didn't think about that, did you? Okay, wait, I got another thing here for you. One more thing, and that is Crazy Hair Day today. I like that. So, Crazy Hair Day today. Oh yeah, baby. It is crazy hair. Crazy hair. Give me a thumbs up if you like that video. Subscribe to my YouTube channel, and you too could have green hair. Yeah, baby. Bye now.